This is the star of all of my videos, my esteemed physics class. They are currently working on their lab finals on the last day of the year before the Christmas break. They have 1 hour and 15 minutes to get this done, and they are all working quite diligently for the most part, as they've been stressed for the past waves for the past couple of days working on this, but it's all gone well. Now, which class is this?
We are Bergkamp. You are physics.
Woo!
I'm actually not physics. My name is Bergkamp, and I'm honored to be one of the semi-finalists for the Shell Award. It's a great privilege. That was my third block class who felt that they needed to be part of the video that I'm going to submit because they have played such a vital role in the filming process, and they wanted to be part of the video, so that was their contribution. The first video that you will see is a set of demonstrations that I do dealing with the concept of energy and how that ties into a bunch of different concepts the kids had studied. So that was a lecture that was given about 90% of the way through the class. So the basic idea of what I was trying to, what you'll see me showing, is this equation here, that delta U equals Q plus W. I'm not sure how up you are in the laws of thermodynamics and terminology, but delta U is the internal energy of the system, Q is the heat flow in and out of the system, and W is work that's done. And again, quick review of your equations. Work equals force times distance, and in this equation it can also equal negative pressure times change in volume. Just so that I'm just giving you those so when you see the demonstration of what I'm talking about, you'll know what's happening. So what I'm trying to convey in that video that you'll see is there's 3 different ways that the kids were showing that you can do work, you can exert a force through a distance to create heat. So the first one, Ali Freeze, is going to be striking a match. Second one, Nick Kuhn, is going to be taking 2 large ball bearings and making them collide around a piece of paper. And then the last one that I'm going to do is what's called a fire syringe, and I'm going to push down on the syringe, and that will eventually make the cotton ignite. So what I was trying to get the kids to see is the big picture connection between what we had studied in terms of friction, in terms of force, in terms of distance, and get that into the concept of energy. And what I consistently tell the kids is that you all understand the concept of energy, but it's tough to quantify and visually represent that. And so those 3 demonstrations that you'll see, what is common to all 3 is that if you go slow, the ignition doesn't take place. If you go quickly, then it does. And so that's trying to reinforce the interconnection between what the kids already know and then the somewhat difficult concept to grasp of this equation of delta U equals Q plus W. Now, when I actually do the syringe itself, it's also an introduction to the ideal gas law, which is pressure times the volume, N is the number of moles, R is the ideal gas law constant, and T is going to be the temperature. And so what I was showing that when I compress the cylinder, that the volume is getting a lot smaller, the pressure then has to go up, assuming that the temperature stays constant. And so that was also a nice way to demonstrate that that ideal gas law constant plays into a compression cycle on an engine. So that's going to be the first video that you see. Hope you enjoy it. All right, so here's the drill. The next phase of this whole journey is what's going to happen in terms of kinetic energy and thermal energy and how all that relates together. So here's the task that 3 people are going to have, me being one of them. So I'm going to have Miss Freeze light a piece of paper using the conventional way of a match. Okay? Now, Nick is going to have a bigger piece of paper. Nick's going to have the big, large ball bearings. Okay? And his task is to burn the paper. And I'm going to have a syringe with a plunger. Okay? And my task is to light paper on fire. Now, so let's start with Adam. What are you going to do to light the paper on fire? You're going to strike the match. Okay? Now, here's what I want you to get the match out. Okay? Now, what I want you to do, I want you to do this very slowly. Okay? I want you to take the match very slowly and push it across the surface. Very slowly. Okay? Now, something is important. When she did that, did the match light? No. Why?
There's no friction, obviously. There's not enough friction.
You say there's not enough friction.
Not enough force applied.
Not enough force applied. But if she did the exact same thing faster, would it light? Rachel? You think? So what's the difference? In both cases, the velocity is the difference, right? Now, is she doing work? Are you doing work?
Yes,
Why?
because I'm exerting a force over distance.
Okay, you're exerting a force over distance, right? You're going to do work. Lovely. Now, so when you do work, what are you trying to create to light the match? Friction. And friction is going to be a form of energy, right? Form of thermal energy, right? Now, imagine this. It was really cold this morning. Let's say that you're standing outside and you don't have your gloves. What are you going to do?
Freeze.
Freeze. You're going to do this, right? You're going to rub your hands together, right? Well, you're going to rub your hands together. Now, when you do that, what are you generating? You're generating heat, right? You're generating friction. You're generating what type of energy? Kinetic or thermal, or both? Thermal, right? You're using kinetic energy to generate thermal energy. Now, what if you did this real slow?
It take a lot longer, or it would create some heat, but not enough to make a difference.
Okay, now, is that analogous to what she was doing with the match? If she moved that very slowly, you're still doing work. You're just doing the work very slowly. Now, here's what happens when you do that slowly, is that that energy has a chance to get dissipated out. She's generating heat, but that energy has time. There's time for that energy to get spread out. Now, let me be your assistant. Okay? Now, I want you to light it like you normally would. Okay? Now, she did the same motion faster. Now it's burning. So now, we can do this.
I was dropped on you.
It's okay. I'm on fire. That's awkward. So, physics teacher up in flames. So, look what I did. I took work and I increased the energy of the paper. And I increased the energy of the paper and the energy of the match enough that this thing caught on fire. Right? Okay? Good. Got that. All right, now, let's go with Nick. Now, Nick has the large ball bearings. Now, here's what I want Nick to do. Okay? I want you to do the exact same process that she did. I want you to bring them together very slowly and hit the paper. Okay? Now, when Nick does that very slowly, how is that similar to what Allie did?
Not enough velocity.
Not enough velocity. With Nick, were you doing work?
Yes,
Why?
because I was moving, I was applying force and direction.
Okay? You were moving, right? You're changing the kinetic energy of it. Now, when they hit, right, Newton's third law, they're going to exert equal and opposite forces on each other. So we're going to take kinetic energy and change that into the thermal energy of the collision, right? Very similar to what Allie did. Allie took kinetic energy, did work, exerted a force through a distance, and lit a match. So it's the exact same idea. Now I want you to do that faster. Okay, do it a couple. Okay, lovely. Now, sounds weird. If I do the smell test, okay, smell like burnt paper? Okay, we've got these nice little holes in the paper. Looks like fringes, right? So Nick did the exact same thing that Allie did. Now, notice that time was a factor. If we did that slowly, the energy got dissipated out, and we didn't have enough to create fire. We do it quickly, we have fire because we've increased the internal energy. Now, what Nick did is that Nick increased the internal energy of the paper by a collision. Allie increased the internal energy of the paper by striking a match and taking that thermal energy and increasing the energy, right? Good so far. Now, my turn. Step in. It's going to get warm, baby. It's going to get warm all up in here. All right. Okay. Yeah. All right. So I've got a little piece of cotton that I'm going to put right here. And then I've got this syringe, or the casement. I'll put that over that. And now I've got a plunger with an O-ring on it so I can create a seal. So now what I'm going to do first is that I'm going to push down very slowly. Now as I push down very slowly, am I doing work? So, Mr. Bartlett, how was what I did here the same as what Nick did and the same thing as Allie did?
Actually, it was velocity. There's not enough velocity.
There's not enough velocity, right? I went slowly, right?
Yeah.
What else is in common?
Doing work.
I'm doing work. Why am I doing work?
Making force over the distance.
Okay, exerting a force over a distance. You see a common thread.
I did.
Now, when I do this, okay, now let's look at the ideal gas law, PV equals nRT. Am I changing the number of moles inside the container? Nope, that's a fixed value, right? Number of moles is a fixed value. Now, if I do this slowly, I'm not going to change the temperature because by doing it slowly, it's like what Allie did. By doing it slowly, I'm allowing that energy to escape out of the system, which is why the match wouldn't light when she went very slowly. Here, it's not going to light because I'm doing this fairly slowly. Now, look at the equation, PV equals nRT. So, if the temperature is going to stay the same, what's going to happen to the right side of the equation? So imagine we have nRT. What's going to happen to the right side of the equation as I push this down slowly? It's going to stay the same, right? Same number of moles, R, temperature is the same. Good? So, but what am I doing to the volume?
Shrinking it.
I'm making the volume smaller, so to get the same NERT, as the volume becomes smaller, what's going to happen to the pressure?
Go up.
Pressure's going to go up.
Can't you create a boil with water?
Hold on. So, if I push down slowly, I do work. I'm decreasing the volume. Now, if I want this little piece of cotton to catch on fire, okay? What's the new movie that came out?
Catching fire?
Yeah, Hunger Games. Okay, so okay. So if I want to catch that on fire, what do I have to do to the internal energy of the cotton?
Increase it.
I have to increase it. Now, Allie could do this. What would Allie do? If I said, Allie, I want you to catch that piece of cotton on fire, what would you do? No. With what you had at the beginning. Yeah, Allie down, strike a match, going, what's the big deal, right? She throws some thermal energy into it. Now, if I gave it to Nick, Nick, what would you do?
Add some kinetic energy.
Add some kinetic energy to it, right? He would smash them together, boom, we could catch fire that way. Now, I don't have either of those. I got stuck with the plunger. So, allowing for what we have seen so far, if I want to catch that on fire, when I pushed it down slowly, I had no flame. So, if we're going to tie all of this together, page the rage, how can I make that cotton catch on fire?
Push it down faster.
Push it down faster so that I can increase the internal energy and hopefully I can make fire. So, let's see if page the rage is correct. So you kind of have, if it works, it'll be a quick flash. Okay? So, yeah, right? So we take that out. Notice that we caught that on fire. Fire! Fire! Okay? Now, do it again. Demanding. Do that again. Put that on there. Boom. Right? So, Paige was right. If I pushed that down slowly, the energy got dissipated out. But if I pushed it down quickly, I increased the internal energy enough to make it catch fire. Good. Got it? Now, here's the deal. When you look at, there's an equation that we're going to talk about, that delta U equals Q plus W. Q refers to energy that's put into a system. Okay? External energy, thermal energy. So, one thing that we could do is that we could take a blowtorch and we could add thermal energy that way, in the form of heat energy. We could do work, okay, by exerting a force through a distance. Either way, I increase the internal energy enough to make that thing catch. The next set of videos you will see are my students from third block working on their comprehensive lab final. This is a lab that I've developed over the years that ties together so many different concepts that the kids have learned throughout the year. So the basic premise is that the kids start with a steel marble that's suspended from a string. It comes down, the thread gets cut by a razor blade. The ball then turns into a projectile and it lands out here on the floor. And you'll see that demonstration of how it works, one of the first things you'll see. So what the kids ultimately try to find is an equation that ties together the height of the marble, how high it is above the floor, and then they use those concepts to determine an equation to predict how far the ball will land. And they're primarily judged on two different criteria: the development of the equation and then the implementation of that, when they actually light the marble, have it cut by the razor blade, and then land out here. So in the course of me working with the kids, I kind of have to let you know what the terminology is, or otherwise what I'm working with the kids won't make a whole bunch of sense. So they have four types of energy that we have dealt with up to that point. You have UG, which stands for gravitational potential energy. You have US, which is the potential energy stored in a spring. You can have KT, which is translational kinetic energy, which is just something just moving. And then you have KR, which is rotational kinetic energy. So that's the vocabulary that that you will hear discussed in the course of me working with the kids. So what I have here, and I know you won't be able to see all of the fine details of this, but this is one of the derived equations that the class came up with. And they started with the idea of conservation of energy, that the sum of all the energies before is going to equal the sum of all the energies afterwards. And then they show things that are canceling out. And then they also then determine the amount of time it's going to take for it to be in the air. So the energy part gets them the velocity of the marble when it gets cut. This part, the kinematics equation, allows them to determine how much time it's going to spend in the air. Then they combine those two equations into range equals 2 times the square root of h1, h2. The kids always enjoy this lab. It's a challenge for them because it ties together so many different concepts that we've talked about throughout the entire year. So that's going to be the videos that you're going to see there at the end. It's a great lab. I have a lot of fun working with the kids, and you'll see me kind of guiding them through the process of arriving at this equation. So when they're initially given this problem, they're not given anything. I give them no guidance. I just tell them they have to come up with an equation. And so then as I work through that with the kids, the light comes on and they go, oh, this is all we have to have. And because they see that different things cancel out, and it ties together all of the different things that we talked about throughout the year. So, hope you enjoy it. Thank you again. Oh, God.
Oh, wow.
Ooh. So what? So was that the mark?
Yeah,
Now, is this
our line
one
was
the other
right.
ones that landed?
Yeah, no, because we moved that paper around.
Yeah, that's
That's just the paper we're using.
Okay.
yeah. That was our new A.
Okay. Here's my question. Stop the bus. Is the paper still in the same plane? In other words, were you always landing left of your mark?
No, we keep moving.
Yeah, the paper keeps moving.
Okay. Well, I didn't know, like, if this was your X, where you thought it was going to land, and then it lands over here left of that point. That's what I'm asking. Like, if you're always left of your mark, then shift your mark left. So, what if that makes sense?
Energy. We kind of
Energy! Gee, we haven't talked about that all class, have we? Okay. You're right, but you were making this horribly... It's okay, you took calculus.
I took calculus.
Okay, you all took calculus.
We're used to this.
And you learned the
We did not take calculus.
Okay.
It's gonna count for something. It's gonna count for something.
It does. Okay. Now stay with me here. Okay? You started off lovely saying you have UGG, right? Why do you only have UGG?
Because it's not moving.
Now, what other forms of energy could you have when it's up here?
Oh, you could have rotational.
You could have KR, you could have
KT.
You could have KT.
Oh, wait, I already said that.
And you could have us.
Us, that's it.
Right? But there's no springs involved, right?
Yes.
So the only game in town up here is now, so here's how you want to start this off. You're going to say UGG plus us plus KT plus KR. Okay? Equals, so you write it down. Okay? You're going to start with all of that. Okay? Lovely. Now, when that hits the razor blade, the sum of all of those energies at the bottom has to equal what? Yeah, the sum of all the energies at the top.
Yeah.
Now, at the bottom, do you have any UGG?
No.
You're UGgless, right? But what do you have at the bottom? Now, why don't you have KR? Not rotating. Why don't you have us? There's no springs. And you have no UGG. So the only game in town is kinetic energy, that is rotational or translational? Translational. Lovely. So you have, what do you have up here? What do you have down there?
KT.
Could you set those two equal to each other?
Yeah.
Oh, fancy! Fancy! Now let's look at this big drawn-out thing that you all have. Actually, let's just act like that's not there. So, up.
Whatever. Rachel's good at it.
Okay, more words in the English language than any other language in the entire world, and you resort to whatever.
Mr. Bergkamp. You can end any conversation. All my attention is focused on this.
Oh, okay, all right.
That defines the end of the conversation.
Here's my point. When you set UGG up at the top, right? That's going to equal
At the bottom.
Yes.
So UG equals what?
KT.
No. Formula.
Oh, yes. No, MGH.
MGH.
I thought you said it right. So
Okay.
Yeah.
MGH, right?
Yes.
Now, KT equals? 10 out of 10 for Rachel. Okay, so, all right, good ones. So, what could you do right away? What's going to cancel out? So you can solve for?
V?
Yeah. Now, so that's going to, what's that going to determine?
The velocity when it lands.
No.
No, the velocity when it leaves
Oh,
the
when it
table.
cuts.
Or when it gets down in that region.
When it gets down in that region. Okay? All right, Beyonce.
Okay, when it gets cut.
Okay.
I'll take that as it flies off. Okay, when it flies.
Now, when it flies off, okay, stay with me here, Miss Calculus. When it flies off, okay, it's the only form of velocity that it has? In the x direction or in the y direction? Y. Yx. Because it's going horizontal. Right? Woo! Okay. Now, when that gets cut, right? Now, after it gets cut, does it begin to accelerate? Why?
Because
Gravity, right? Now, gravity is only going to cause an acceleration in which direction?
Vertical. I was thinking this, but I said the other one. I know what I'm talking about.
Why?
I know what I meant.
Okay. Lovely? Now, here, you can redeem yourself. Why isn't there a horizontal acceleration? There's no horizontal.
Bam. Party.
Woo! Okay? Lovely? So, what type of problem involves something flying off with no vertical direction and only horizontal direction?
Projectile.
But which type of projectile?
Lemming.
Lemming problem.
I think I missed that on the test.
Now. Because you have a constant horizontal velocity, what equation can you use?
This
T equals that one.
Oh,
That's the one.
Yeah.
I'm looking for a T equation.
what is this?
That is finding
What does the little t give you
time. It takes
to go from where to where?
there,
the top and that.
there, yeah.
To the bottom.
To velocity final is zero. No, not zero. Yes.
Maybe the distance to fall,
Yes.
Sure. Yeah.
right?
Yeah.
The distance to fall. Let's go with that. Okay. Now, what's the only time you can use time equals the square root of 2y over g?
If your initial
Which velocity is 0? It's a very specific. I know that. In the x direction or in the y direction?
The Y direction.
Now do you see why it has to be cut at the bottom?
Yes.
Because if you don't cut it at the bottom, what does it have?
It has some.
has
I mean,
Articulate. Rhymes with velocity in the y direction.
velocity.
velocity.
Very good. Very good.